We're going to start off with Chapter 2, Radiation Concepts. Your objectives include: describe the fundamental atomic structure, describe the electromagnetic spectrum, describe wavelength and frequency and how they are related to velocity, explain the relationship of energy, wavelength, and frequency, explain the wave-particle duality phenomena, identify the properties of X-rays, describe the processes of ionization and excitation, describe particulate radiation, differentiate between ionizing and non-ionizing radiation, describe radioactivity and radioactive decay in terms of alpha, beta, and gamma emission, discuss relationships of wavelength and frequency to beam characteristics, compare and contrast different types of radiation, and differentiate between ionic and covalent molecular bonds. Radiography is both an art and a science. The scientific method is used and is important to understand the world we live in. The scientific method involves collecting facts, studying their relationships, and arriving at conclusions based on analysis. Now, as radiographers, we're going to learn both about physical and biological science. Physical science is the study of non-living matter. An example would be physics, which is what this course is mainly going to cover. Biological science is the study of living matter. Those courses would include anatomy and physiology. Physics studies relationships between matter and energy. Matter has mass and occupies space. Radiation is emitted energy that is transmitted through matter, and energy is the force used to do work. The unit of energy is the joule. There are a few other units we're going to talk about later in this chapter that also measure energy. Hopefully some of the things we're about to talk about will refresh your memory from old physics courses you may have taken. So first we're going to talk about matter. It's the substance that comprises all physical objects. It has a shape, takes form, and takes up space. Mass is the quantity of matter contained in an object. And mass, the unit that measures mass, is the kilogram. And there is a difference between mass and weight. They're two different concepts. Mass is the quantity of matter in an object. The force that an object exerts under the influence of gravity is weight. For example, in space you could be weightless, but you would still have the same mass as you would on Earth. Matter is most commonly found as a mixture of substances. An example would be air. Substances can either be simple or complex. Typically, simple substances are known as elements, and complex substances are known as compounds. Now, atoms are the smallest particle of an element, which possess the chemical properties of that specific element. When two or more atoms unite, they form a molecule, which is the smallest particle of a compound. An example of an element is hydrogen, and an example of a compound would be H2O, which we know as hydrogen, and oxygen, which is water. And a mixture is formed when two or more substances are combined. Here's just a visualization of how a mixture is broken down into a substance, and how a substance, simple or complex, can be both broken down into an element and compound, and then further broken down into an atom and a molecule. Okay, so this slide is, again, what we've talked about. Goes into a little bit more detail. So the smallest part of an element is an atom, is the smallest particle of an element that still possesses the chemical properties of that element. And then a molecule is the smallest particle of a compound possessing the characteristics of that compound. Matter can be found in three different states: a solid, liquid, or gas. This is going to be dependent upon varying degrees of molecular attraction, which is largely due to temperature. Water is a great example because we know depending on its temperature, water can be a solid, liquid, or a gas. Energy Energy, as we've already defined, is the ability to do work. The unit of energy, as we saw in one of the first slides, is the joule, but I want you to also write down that volt, or voltage, also measures energy. When energy is emitted and transferred through matter, this is called radiation. There's different types of radiation that we're going to discuss in this course as well. So you have radiating light, an example would be a light bulb, and radiating heat, an example of this would be a stovetop. Energy can be broken down into what we call photons. Now when we start talking about X-rays, we refer to them as X-ray photons because those are bundles of energy. Also, energy does not have a mass, and energy does not have a charge. So keep these two things in mind when we go further into the chapter. Albert Einstein described the interchangeable relationship between matter and energy. He described this mathematically as E equals mc squared. E stands for energy, m stands for mass, and c stands for the speed of light. And this relationship is the basis of nuclear power. His theory states that matter and energy cannot be created or destroyed, but can change form. So his theory of relativity states the sum total of all matter and energy in the universe is constant. Matter cannot be created or destroyed, but can be converted from one form to another. Although recent research has disproven this theory, it is still essentially true. The ancient Greeks theorized that there were four components of matter: air, water, earth, and fire. They named the smallest element of these four components the atom. After that, in the early 1800s, John Dalton separated the elements based on their mass. He determined that each element had atoms that reacted identically during chemical reactions. Eventually, this led to Mendeleev's development of the periodic table of elements. Here is a visual of the periodic table of elements that Mendeleev created in the mid-1800s. In 1911, Rutherford, a physicist, determined that an atom had a dense positive nucleus surrounded by a cloud of negative electrons. However, his theory did not have a structure to it. So therefore, 2 years later, Bohr, another scientist, expanded on his theory and determined that an atom simulates a miniature solar system, but still had that nucleus surrounded by orbiting electrons. Schrödinger set the foundation of modern physics. He was known for his concept of quantum physics, or wave mechanics. According to his principle of quantum mechanics, orbital electrons are assigned probabilities for occupying any location in an atom. The greatest of those possibilities are associated with Bohr's model. The nucleus of an atom is a small, dense center. The nucleus contains nucleons, is known as protons, which have a positive charge, and neutrons, which have a neutral charge. Electrons orbit the nucleus in a variety of planes. According to quantum physics, electrons cannot be divided, and protons and neutrons are made up of quarks. This is all according to the M theory, also known as the string theory. The M theory is a concept that links quantum physics and relativity. It implies that electrons and quarks may not be particles, but may be small loops of rapidly vibrating string-like matter, for example, like a vibrating guitar string. This is now called, again, the string theory. Now, this also proposes new dimensions in addition to the 4 dimensions that are already known, also known as wormholes. We can watch this video after this presentation. As we have stated, the basic atomic particles include protons, neutrons, and electrons. Of course, protons are positive, neutrons are neutral, and electrons are negative. If you look, protons and neutrons are very similar in mass. They both weigh about 1 kilogram, versus an electron is essentially zero mass because it is so small. When discussing atoms, there's something called electrical stability. Electrical stability is maintained through an equal number of protons and electrons. Z number, also known as atomic number, distinguishes elements by the number of protons contained in the nucleus. Whenever you change the Z number, or the atomic number, you're actually changing that element. An example of this is radioactive decay. Radium has a Z number of 88. Through radioactive decay, emits an alpha particle. When the alpha particle is emitted, that actually decays to a new element called radon, which has an atomic number of 86. Alpha particles, beta particles, and gamma radiation are all emitted during radioactive decay. Alpha particles are positive, containing 2 protons and 2 neutrons. Alpha particles can only be damaging when internal contamination occurs. That would be if an alpha particle was inhaled, ingested, or injected. Beta particles are a type of electron emitted from the nucleus, and these can actually be positive or negative. Gamma radiation is a type of electromagnetic radiation that originates from inside the nucleus. Half-life is used to measure radioactive decay. So here's an example problem, as we're going to have some math to go along with this. How much activity will remain in a dose of 40 millicuries of iodine after 10 hours? T sub 1/2 equals 2 hours. So that means the half-life is 2 hours. So we're going to start at 40 and half every time until we get to 10 hours. So we start at 40, half that is 20. So going from 40 to 20, 2 hours have passed. Another 2 hours, we're now down to 10 millicuries. Another 2 hours, we're down to 5 millicuries. After 2 more hours, we're down to 2.5 millicuries. And finally, 2 more hours, equaling 10 hours, we would be down to 1.25 millicuries. So 1.25 would be your final answer. Also, see the snippet uploaded in Canvas of me working more of these problems. This pie chart is the NCRP report number 160. Half of this chart is made up of natural radiations. The other half are man-made. Terrestrial, internal, space, and radon and thoron are all natural, while CT, nuke med, interventional, conventional radiography and fluoro, consumer, occupational, and industrial are all man-made. Radon takes up the most at 37% of this graph. Radon is naturally occurring and can be found in homes. That's why we have radon testing. And then CT makes up 24%, or the majority of the man-made radiation sources. Changing the number of neutrons or electrons does not necessarily change the element. Isotopes have the same number of protons but different number of neutrons. Ions are atoms that have gained or lost an electron. Ionization is the term used to describe this process. Ionization is an important term in our field because we work with ionizing radiation. Changing the number of neutrons changes the atomic mass only, not the element. Change in electron number does not change the element, as number of protons remains unaffected. Ionization is the addition or removal of an electron from an atom. X-ray photons can interact with an atom, and this can result in the ejection of an electron, therefore creating ionizing radiation. This also changes charges between atoms. Again, ionization occurs when an X-ray photon kicks out an electron of an atom. Ionization of atoms can cause disruptions in the body's metabolic relationships. Exposing patients to ionizing radiation can produce short-term and long-term effects. This is why, in order to take an X-ray, this requires an order from a licensed practitioner. Here's a visual on the process of ionization. Note that ionization does not change the Z number, and therefore the element remains the same, but the charge is going to change. So on this image, you can see that an X-ray photon is coming in to kick out an electron, and this is a neutral carbon atom. Once that electron is kicked out, it is now an ionized carbon atom. Atomic mass is concentrated in the nucleus. Just as a review, you can see the mass of a proton and neutron are very similar, while the mass of an electron is much lighter. The atomic mass number is also known as the A number. Don't confuse it with the Z number. Z number is just the number of protons in the nucleus. The atomic mass number is the number of protons and neutrons in the nucleus. This neglects the mass of the atom's electrons because they are so small. Orbital electrons are located in shells. The shells are labeled K, which is the innermost shell, all the way out, L, M, N, O, P, Q, and so forth. As you can see, each shell has a designated number. K equals 1, L equals 2, M equals 3, and so forth. The electron capacity of each shell is measured with the formula 2n squared. N indicates the orbital shell number. Electron binding energy results from positive attraction of the nucleus to the electron. The closest shell, or the K shell, is the most tightly bound because of that positive nucleus. There is energy needed to eject an electron from an atom from those shells. The binding energy is going to be dependent upon how close that electron is to the nucleus. The electron binding energy increases as the Z number of the element increases. This visualization to the right is a tungsten atom. As you can see, the K shell is 69.5 keV. As we go out through each shell, through L, M, N, O, and P, you can see that the binding energies decrease. Electron binding energy is determined by two factors: the electron proximity to the nucleus and the number of protons in the nucleus, or the Z number. The unit is electron volts, or eV. This is the energy of one electron when accelerated by 1 volt. Understanding electron binding energy is a key concept in radiology physics. Here's an example math problem of determining the maximum number of electrons in a shell. So the electron capacity is measured as 2n squared. What is the maximum number of electrons allowed in the M shell? If you look at a previous slide, the M shell is number 3. So you would plug in 3 in place of n. 3 squared is 9, times 2 is 18. So the maximum number of electrons allowed in the M shell is 18. The octet rule is the number of electrons in the outermost shell will never exceed 8 electrons. The atom never has more than 8 electrons in the outer shell. For this reason, some atoms begin to fill in the next shell before the maximum is reached. An atom with 8 electrons in the outer shell is considered chemically stable or inert. This image demonstrates how the increase in Z number increases the binding energy. Hydrogen, which is the lowest on the periodic table, the lowest Z number, only has a binding energy of 0.02 kiloelectron volts. all the way up to lead that has 88.01 kiloelectron volts. Let's talk about the periodic table of elements. In the upper left-hand corner, you can see that the elements are listed in ascending Z-number order. Not only are elements arranged according to their atomic number, but they're also arranged in families and groups. These are called vertical groups and horizontal periods. Vertical groups have the same number of electrons in the outer or valence shell, while horizontal periods indicate elements that have the same number of electron shells. The atomic nomenclature identifies the atomic element symbol, the atomic weight, and the Z number. Again, horizontal periods indicate the elements that have the same number of electron shells, while vertical groups have the same number of electrons in the outer or valence shell. The chemical behavior of an element is determined by the valence band, or the outermost shell. Chemical combining characteristics describes how atoms will bond with other atoms. So valence plus 1 means that there is one electron in the outer shell, which means the atom will likely give up that electron. Valence minus 1, or negative 1, means that there are 7 electrons in the outer shell, meaning that the atom will likely gain that one electron. In an ionic bond, an electron from an atom with a valence plus 1 will give up that electron to an atom with a valence negative 1. In this image, you can see a sodium atom has an electron, or a valence plus 1, in the outer shell. The electron is transferred to a chlorine atom that has a valence of negative 1. Or you can see 7 electrons are in the outer shell. Once that electron is transferred, this atom becomes a chloride ion. A covalent bond is a little bit different from an ionic bond. In a covalent bond, the valence plus 1 and valence negative 1 atoms come together by sharing the electron and becoming a compound. For example, in this image, water molecule H2O. Instead of giving up an electron, these atoms share electrons. Energy is the ability to do work. The physicist's definition of work is the formula work equals force times distance, which is the force acting upon an object over the distance expends energy and is considered work. Mechanical energy is the action of physical movement. There are 2 types. Potential energy has energy due to its position, or energy at rest. An example is a car at the top of a hill. This has potential energy of rolling forward and rolling downhill. Kinetic energy is known as the energy of motion. Chemical energy is energy that is released from a chemical reaction. For example, a battery converts chemical energy into electrical energy. Heat energy is also known as thermal energy and results from the movement of molecules. Temperature measures thermal energy. For example, X-ray production produces high thermal energy. Electrical energy occurs within the conduction band in an atom and results from movement of electrons in a conductor. For example, a light bulb changes electrical energy into light. Nuclear energy is obtained by breaking bonds between particles in the nucleus. Nuclear power plants convert nuclear energy to thermal energy and eventually into electricity. Electromagnetic energy, or EM energy, is the combination between electric and magnetic fields traveling through space. Electromagnetic energy is important to us because X-rays are a type of electromagnetic energy. It is a natural part of the environment, and its nature was discovered through studying light, which also lies on the electromagnetic spectrum. This led to the study of invisible forms of EM. The range of energies is presented on the electromagnetic spectrum. All electromagnetic energies have different frequencies and wavelengths, but they all travel at the speed of light. The speed of light will never change. EM energies of 10 electron volts and higher are considered ionizing radiations. Here's an example of the electromagnetic spectrum. As you can see, energies above 10 electron volts include high energy ultraviolet, gamma rays, X-rays, and cosmic rays. We will watch this video at the end of the presentation. This is another chart of the electromagnetic spectrum that you should study. This one's a little bit easier to study from, but you need to know the order that these radiations lie. So starting at radio frequencies at the lowest, microwaves, infrared, visible light, UV, X-rays, and gamma rays. This chart shows you the energies, frequencies, and the wavelengths. As we just stated, the three characteristics of electromagnetic radiation include energy, frequency, and wavelengths. Wavelength and frequency have an inverse relationship, meaning that the higher the frequency, the shorter the wavelength. According to the wave theory, the waves are disturbances in a medium, for example, the ocean, sound, and so forth. Wavelength is going to be represented by the angstrom, and frequency is represented by V. Frequency is measured in cycles per second, or hertz. We're going to take the wave theory and put it in wave equation. Frequency and wavelength are inversely related. The equation is velocity equals frequency times wavelength. Remember that the velocity of all electromagnetic radiation is the speed of light, represented with a c. c, or the speed of light, equals 3 times 10 to the 8th meters per second, and this will never change. So the wave equation formula is c equals v times the angstrom, or velocity equals frequency times wavelength. You can see a snippet uploaded in Canvas of me working these problems. Personally, instead of using V, I use F to represent frequency. The particle theory is also known as the wave-particle duality phenomena. This theory states that high frequency, high electromagnetic radiation, like X-rays and gamma rays, can interact like particles when contacting matter, although these energies are not actually particles. Remember, particles have a charge and a mass, while electromagnetic radiation does not. So even though they are not particles, they can interact with matter as if they were particles. A small bundle of energy is the photon. Again, no charge, no mass. Photon energy and frequency are directly related. If frequency is doubled, energy doubles. As you saw on the previous slide at the bottom, there is a formula, E equals h times v. This is Planck's constant. Planck, or Max Planck, was a German physicist who explains the relationship between photon energy and frequency. Planck's constant equals 4.15 times 10 to the negative 15th electron volts per second. You can also see these problems worked out in the extra snippet of math problems in Canvas. We can visit this website after the presentation. X-rays were discovered by Wilhelm Conrad Röntgen on November 8, 1895. He was the first Nobel Prize winner for physics in 1901. He discovered X-rays while studying the behavior of electrons traveling through a gas tube. He also identified the use of barium platinocyanide as a fluorescent material. The first X-ray was his wife Anna's hand with the ring on her finger, and you can see her bones demonstrated in the image. You'll need to memorize the properties of X-rays. These include that they are penetrating in an invisible form of EM radiation. X-rays are electrically neutral. They are polyenergetic or heterogeneous energies. They release heat when passing through matter. They travel in straight lines. They travel at the speed of light. They can ionize matter. They can cause fluorescence in certain crystals. They cannot be focused by a lens. They can affect photographic film. X-rays can produce chemical and biological changes in matter through ionization and excitation. And X-rays can produce secondary and scatter radiation. This is the end of the Chapter 2 Radiation Concepts presentation. Please visit the Test 1 module under the Canvas course, and you should see a page called Video Links. Those links will include the video links in this presentation, video links of myself working the math problems that you'll need to know, as well as a YouTube link of this presentation with closed captions.